Okay, so we want to take a look at how we're going to use the process of proving by contradiction to show that the square root of one of our prime numbers is an irrational number. So we're going to take a look at maybe root 2. So we want to prove that root 2 is irrational. Okay, we want to do so by a very particular process, a process that we call the process of proving by contradiction. Now, if I want to prove this by contradiction, what that means is I have to assume that the opposite to that statement is true. So I have to assume that root 2 is a rational number. And what does that mean? Well, from our study of rational numbers, it means I have to assume that root 2 can be written as a fraction, a over b, where a over b is a fraction written in its lowest terms. Okay, so the first thing we do is we assume that root 2 is rational. Okay, now what does that mean? And again, it's very, very good to explain what you mean by root 2 being rational in terms of symbols, where root 2 is equal to a over b, all right? Both a and b are elements of the integers. B cannot be 0 because we can't have 0 as a denominator. And finally, we could say that the HCF of a and b is 1. Now, it's the final part of that statement that's all important, because if root 2 is rational, well, then that means that the fraction representing root 2 will be written in its lowest terms. So therefore, you'll have something like 3/4, or you'll have something like 7/8. It won't be further simplified, okay? The common factor between the numerator and the denominator will be 1. Now, let's go for a bit of mathematics here. If we've made a statement and we're assuming that root 2 is equal to a over b, so if root 2 is equal to a over b, normally in mathematics, we always say clear the symbols and clear the fractions. That's exactly what I'm going to do here, and I'm going to do it in that order. So I'm going to square everything, both left and right. So we square the left-hand side, we get 2. And if we square the fraction on the right-hand side, we get a squared over b squared. And then you clear the fraction. That means you multiply both sides by b squared. So you get 2b squared is equal to a squared. Now, this is the important thing. They're telling me that a squared is some multiple of 2. So this is telling me that a squared equals 2 times something, all right? And there is a rule in mathematics that says that if your square is equal to 2 times something, then its root will also be equal to 2 times something. Now just take 100, for example. All right? If 100 is equal to 2 times 50, so 100 is a multiple of 2, then its root, 10, will also be a multiple of 2, because it's 2 times 5. Now, notice that the 100 is 2 times 50, and 10 is 2 times 5. So therefore, if a squared is a multiple of 2, then a will be a multiple of 2, but they'll be different multiples of 2. So in that case, we're going to say the following. If a squared is a multiple of 2, then a is a different multiple of 2. So you're going to use a different symbol after the 2 to show that a is a different multiple of 2. What symbol can I use? Anything you like. Square, circle, use another letter, use a star, use whatever you want, okay? But the key thing is that you've shown a squared is a multiple of 2, then a is a different multiple of 2. So that's why we have to use a different symbol after the 2 here. Normally, I just choose x. So if a squared is a multiple of 2, then a, which is the square root of a squared, obviously, is also a multiple of 2, albeit a different multiple. Okay, so those two results there are extremely important. Number 1, because we know in the first statement what the relationship is between a and b. And secondly, the second statement gives me a new way to write a. A is equal to 2x. Now, if a is equal to 2x, we can substitute that 2x back up into equation 1. Therefore, this is going to give me 2b squared is equal to 2x to b squared. All right, working that out, 2b squared is equal to 4x squared. And then you can divide both sides by 2, just normal algebraic processes. B squared is equal to 2x squared. So what's that telling me? This is now telling me that b squared is a multiple of 2. Now, if b squared is a multiple of 2, then b will be a multiple of 2, and it will be a different multiple of 2. So therefore, if b squared is equal to a multiple of 2, then b is going to be a multiple of 2 also, albeit a different multiple of 2, so we just call that 2y. And there's your second result. All right. Now, what did we assume at the beginning of this particular process? We assumed that root 2 was equal to a over b, where the fraction a over b would automatically be fully simplified. So if I take a here, and I take b, and I put a over b, I get 2x over 2y, which is not fully simplified. So the process has told me that when you put a over b using root 2 as your number, it reveals a fraction that does not have the HCF as 1. In other words, it's not fully simplified. So that means that the HCF of a and b is actually 2. And that's where the contradiction takes place. You're now contradicting what you said above, that root 2 would be a over b, where a over b would give you a fraction that is fully simplified. A over b, in fact, gives me a fraction that can further be simplified. So you've contradicted yourself. And because you've contradicted yourself, therefore, your assumption is false. Assumption false, which means root 2 is irrational. And you can do exactly the same thing with root 3 and root 5 and root 7 and root 11 and root 13. And that's what I would ask you to do. So try the whole process again. The next time, try and prove that root 3 is irrational by contradiction. Then try and prove that root 5, root 7, root 11, and so on. And see that the same process will give you exactly the same result. Okay? It's interesting to note that when I want to prove that root 2 is irrational, when I form my fraction between a and b, the common factor in the numerator and the denominator is 2. So if I wanted to prove that root 3 was irrational, then the common factor in your numerator and denominator down here would be 3. If I wanted to prove that root 11 was irrational, then the common factor over a and b would be 11. So therefore, there's a link between the number that you're working with in the start, the irrational number, and the number that will appear in the numerator and the denominator of the a over b fraction when we form it at the end.